All right, good morning, everyone. I'm Chad Herring. I'm the Central Region Sales Manager at Bell Lumber and Pole Company. Kind of out of my normal element, talking at an environmental conference as a sales rep for wood utility poles, but I've been with the company for 13 years. We're a fourth generation family owned business that's been manufacturing and treating wood structures to the utility industry for over 100 years. And the reason why we're here today is, the very aggressive goals that the industry has striving to reduce the overall carbon emissions. And, most of the focus has been on power generation, rightfully so, because it's probably the biggest contributor. But with the goals that are out there, it's really going to take a pretty balanced approach in all aspects. And I think, utilities have done a good job of educating consumers on how their buying behaviors can make a positive impact on the environment by reducing their demand for energy, like energy efficient appliances or LED lighting and so forth. And that's really what we're going to talk about today, is just another tool in the tool belt, right? Summing up how these decisions on what structure you're using on the utility lines can make a positive impact on the environment. So with that, there has been a trend in the utility industry over the last couple of decades of transmission lines moving away from wood to other materials such as steel. And that's really what we're looking at evaluating here, is taking an objective comparison of the perceptions of those materials versus how they're actually performing in the field. And in doing so, we looked at 5 different categories. The most important today that we're here to talk about is the environmental impact and carbon footprint that the structures can have, but also the material life expectancy, including inspection and maintenance, line hardening, availability, sustainability, and lastly, the lifetime cost. So we start with the environmental impact. Aquatier did a life cycle analysis, I think it was in 2013, regarding 4 different materials, one being a treated pole, one being concrete, one being steel, and then composite. And looking at the energy requirements over their life cycle analysis. And I'm going to point out just one particular portion of it right now is really the net greenhouse gas effect. And the only material that has a negative impact on greenhouse gases is the wood structures. So, there's a lot of different varying degrees of, what's one of the major contributors to emissions in the world, but the manufacturing of concrete and steel products account for about 16% of that. And that demand is continuing to grow. Our point here today is there's a time and place for all these materials, but when you have a structure where you can use wood, you should, for the reasons that I'm going to talk about today. There'll be reasons why you need to use steel and concrete when you start getting into 500 kV and larger. So again, really the focus here is that balanced approach. So the wood industry, for the most part, we've been around since the start of the utility industry and really haven't done a good job of promoting why you should, continue to use wood. We've done a good job over the last 5 years coming up with a lot of different resources to help utilities understand the use of wood and the impacts of it. So this technical bulletin was produced by the North American Wood Pole Council. That council's got several technical bulletins that I'll reference here today, but this one is talking about the calculating carbon in the wood utility pole cross arms and wood poles. And they're talking about what is the only building material that is carbon positive. So while trees are growing in the forest, through the process of photosynthesis, CO2 is removed from the air and converted into wood and free oxygen. So when those trees are harvested for long-lasting products such as treated wood utility pole, that carbon is stored for many decades, typically 70 years or more. And that long-term storage is called sequestration. So that sequestered carbon is not CO2 in the air contributing to climate change. And in addition to that, while that tree is now a utility structure for 70 years, there's additional trees growing in the forest, removing additional CO2. Sustainable, renewable, it's the life cycle. So how do we take scientifically derived data and help utilities promote when they use wood, how they're affecting, having a positive impact on the environment? And this bulletin came along with the carbon sequestration calculation and summary based on scientifically derived data. Really easy to use. You put in the quantity. In this case, we just put in 2,000 60-foot Class H2 wood poles. The summary comes out to about a little over 4,000 metric tons of CO2 is sequestered, which means absolutely nothing to the common individual. So for a utility to advertise that in the website, probably not going to get much relatability there. But if you go to the EPA's website, they got the greenhouse emissions calculator there, what I would call a translator. If you put in that 4,000 metric tons, it'll spit out probably 10 different relatable scenarios. I just picked out 2 here. So that 4,000 metric tons would be equal to 10.2 million miles of greenhouse gases emitted by vehicles, for example. Now, on this particular slide, I used general information on, the manufacturing, again, of steel products is going to create carbon. And so based on per ton, here on published data, we estimated that 2,000 60-foot H2 steel poles are probably going to produce right around 1,500 metric tons of CO2 versus wood sequestering it. And that would be equal to about roughly 3.4 million miles of greenhouse gases emitted by vehicles, or over 156,000 gallons of gas being consumed. So in summary, that carbon footprint, again, we're looking at the same 2,000 structures. Wood's going to sequester 4,000 metric tons, where steel is going to produce 1,500 metric tons. So this line, if a utility chose to use steel versus wood, the net impact is going to be over 13.7 million miles of greenhouse gases emitted by vehicles, over 616,000 gallons of gas being consumed. So now, looking at how wood utility structures, when used, can have a positive impact on the environment, really looking at the other factors that utilities use to evaluate, choosing what structures they should use in their line design. So that's really what the remainder of the presentation is about. And probably the biggest factor in everything that's going to be compared when utilities are looking at structures is the cost analysis. And in that cost analysis, it's all going to come down to the assumptions made on life expectancy. The steel and concrete industry have a consistent message out there of wood poles that are treated will last 30 years versus their material lasting 80 to 100 years, therefore justifying 2 to 3 times the cost for that particular structure. But what we're looking at today is we're not comparing materials of which one's better than the other. We're just asking for a fair comparison based on how the materials are actually performing in service. And so the first resource we're going to look at is Osmos Utility Services. For those of you that are familiar, they're an inline inspection company that inspect both wood poles and steel structures. And we use them quite a bit in this presentation as well. And in this slide, what they were trying to find is what the average reject age of a treated wood utility pole. So a manufacturer like Bell treats a utility pole, the utility goes and installs that. Without any inspection or remedial treatment in place in the field, how long is the average life expectancy going to be for that pole? And so they looked at over 6.5 million unique pole inspection records across the United States, so several different decay zones and areas and environments. Important to note, this was the first time those poles were inspected. They were inspected 18 inches below grade and all the way around the entire circumference of the pole. And what they found was, for example, in the moderate area here, this medium color, they're looking at the average average reject age was over 47 years. So that's significantly higher than 30 years. But again, this isn't taking into fact you're doing any inspection or remedial treatment out in the field. There was a different information that came out from Osmos where they looked at 750,000 unique pole inspection records and try to compute what that average.
I guess most of those were creosote as well, I would imagine.
It's a variety of treatments.
Yeah, variety of treatments. Okay,
yep.
So it's across the spectrum.
That's correct. So variety of treatments, variety of species. It's a good point, but it doesn't differentiate. The study doesn't say specifically. So when you're looking at that, sorry, I lost train of thought. 750,000.
It's just whatever's in place and they're inspecting.
Yep.
So there's a variety of, because I know, like the older ones are probably going to be creosote, where some of the newer ones are going to be CCA, just because that's the general trend of what's going on.
Correct.
And now you've got the phenolic compound ones.
dichlorophenol, DCOI, CCA. You got different ground line preparation, back in the original, when they started using Douglas fir, there was never any ground line prep. Now you do radial drilling through boring,
Right.
a lot of different things to help. Yep.
That helps too.
Yep. So there's a lot of different factors in there, but in average, this is what they found what the reject age was.
So what is a reject?
A pole has to be replaced. So the pole, the inspector comes out, looks at it, and
So
that
does
pole
that
is-
account for, like a road widening where they're taking those out?
It's an
like,
excellent
regardless?
point. The next slide will show that, how that can impact this. There's a lot of different things that impact it, but here, this is strictly looking at, so Osmos is going out and paid by the utility to inspect their poles. So they're looking at poles. This has nothing, this wouldn't include like road widening and stuff.
Okay.
This would be strictly they're inspecting the pole and saying, hey, this one needs to be kicked out. Because the decay, it's beyond the tolerances, we gotta change out this pole. It's a good point. We'll talk about that a little bit later, but it's an excellent point. So this was just basically the average reject age with nothing being done to the pole. When they looked at 750,000 pole inspection records and try to compute what that reject or the average life expectancy would be with remedial treatment in place, the maintenance and inspection, that predicted life would be beyond 100 years. So it's debated, you know what I mean, depending on the level of remedial treatment and all that kind of stuff that you do. But, so again, that whole idea of a treated wood pole is gonna last 30 years it's just not accurate. Whether you do anything with the pole at all or not, but then let alone try to prolong that life of that pole. And to the point here, there's a whole technical bulletin based on this whole subject of the estimated service life of wood poles, because honestly, the perception is just wrong for the most part when you start talking about what other manufactured
It's
products
closer
are
to
talking
50
about.
instead of 30.
Correct, yes. And so the other factor is like the gentleman said here, is a study that was done in 2006. It wasn't a study, it was a survey of utilities in the Pacific Northwest, where they had to categorically list why they changed out wood poles. And what they found was 38% of the pole removals, wood pole removals, had nothing to do with the structural integrity of the pole. Just road widening, line upgrades. I mean, when you think about when the utility industry started, wood was here, right? Wood's been around forever. But how many times have our infrastructure changed? Roads, clearances, heights, voltages, all that's changed. Well, that's all, if you factor in how many times they replace poles, that has a big part of that. So it's just something to keep in mind. It does skew the numbers.
It's a pretty high percentage.
Yeah, it's a really high percentage. And again, we don't know, as a whole, how much that percentage is, but we just know it's a percentage. We know that it is a factor. So on the flip side, the life expectancy is steel. Like a lot of people, when it first came out, and even now, people, when they're evaluating steel, it's set it, forget it, you don't have to worry about it. They're not including maintenance and inspection costs. Don't need to, it's steel. It's gonna last 80 years. Well, the reality is that is not the reality of what's happened in the field. And so I'm gonna cite a couple different sources. I won't name all these just because time constraints and whatever, but Material Performance Magazine is the world's largest magazine in circulation exclusively dedicated to corrosion prevention and control. And so I'll cite them a few times in here. And in the top left-hand corner, they talk about the deteriorating factory-applied coatings can become detrimental to the structures because they not only allow moisture to come in contact, they actually hold moisture against the steel, accelerating the corrosion process. The best that summarizes everything up regarding the perception of steel is this next quote, really, that came from Osmos Utilities steel literature, talking about once thought to be permanent structures free from maintenance reliability concerns. Steel structures demonstrate they do indeed degrade over time as a result of corrosion and mechanical damage. Later on, it's not on the slide, but later on in that informational packet, they talk about age alone is not an accurate predictor of which structures are going to be experiencing corrosion. What's that mean? You have to have your routine maintenance and inspection. You have to do that. And people need to start including that in their evaluation. So even in the steel companies manufacturing and installation, and they talk about all finishes are subject to gradual deterioration. Ongoing maintenance program must include periodic inspection for abnormal corrosion. And the maintenance program should include observation for excessive vibration, examination for structural damage or bolt loosening. I say that really fast because you guys don't want to sit and listen and read. But when I'm talking to a utility, and the utility is looking at a 69 kV line, and they're looking at a different steel structure that's gonna cost twice as much. The reasoning, sometimes, the reason is, well, it's going into a private right-of-way and we just don't have access to it. Set it and forget it mentality, right? I'm gonna set a steel structure or something besides wood, I ain't gotta look at it. And that's not the reality. Material Performance Magazine here, this article is talking about assessing galvanized steel poles and towers. Typically, a structure won't need to be top coated until a significant portion of the galvanizing surface zinc is depleted, which could take 30 to 40 years. 30 to 40 years. So it's not a matter if it's going to need to be top coated out in the field or remedial treated, it's when. Osmos came out with a white paper within the last couple of years. Corrosion wave demands attention. Quote, same situation, galvanization may age out in less than 30 years below grade, leaving steel vulnerable to corrosion just after 40 years or less. Consistent based on actual performance in the field. So here's a great summary of this right here. T&D World, I think it was in November 2011, a public power provider in the state of Ohio, built a 69 kV line. They chose to do it with weathering steel back in the 1970s. In the article, they talk about the reason why is because the reason why they went to weathering steel is those poles were thought to be maintenance-free material. But now we know there's no such thing as a maintenance pole or tower, right? So they didn't do anything to the structures for almost 50 years. A pedestrian was walking by the poles, noticed a crack in one of the poles. Well, that caused basically a full corrosion assessment program of that entire line. What they found was it brought to light the true nature and extent of the problem. Out of the 109 poles for that line, 70 of them required some level of intervention like this. And some of them actually need to be replaced. So here, the set it, forget it, pay double for it, and now look at, nothing's perfect. Mother Nature's gonna wreak havoc on everything one way or another, right? Now we'll get into more of, the other concerns with utilities. Harden your system, be more resilient, be more reliable. So here's a book that was published over the last couple of years, Wood Pole Structures for Electric Transmission Lines. And I'm going to use their definition of resiliency, which is the ability of a system to withstand extreme weather events to minimize the number, extent, and duration of outages. So this is important. So when you look at outages over a 10-year period of time, they look at 2002 to 2012. 50% of the outages were caused by severe weather, which really isn't very shocking. I mean, it's pretty, you'd anticipate that. But outages that affect more than 50,000 customers, 80% of those are caused by severe weather. Now, one of the misperceptions is replace a wood pole with a steel pole, you're going to harden your system. And this book addresses that changing structural material alone is not an effective hardening strategy, that the design criteria for loading and strength must also be changed in order to significantly improve line resiliency through structure replacement. Line hardening. So the unique overload capacity of wood poles when we talk about these big storm events. Important to keep in mind that widespread failure is not going to occur unless the actual load, the design load, is exceeded, right? That can happen because overload conditions can happen because of fallen trees, wind-blown debris, just a very, very severe storm. Ice, yes. So you want to compare a couple different materials. Engineers today, I'm not an engineer, would want to compare two different materials. They would design both of those materials to a 5% lower exclusion limit, which would be 95% of those materials will exceed the design strength, okay? This closely represents the design equivalency and grade deconstruction of the National Electric Safety Code, which applies a safety factor wood of 65%, which 5% LEL on wood would be 67.1. But back to the design equivalency, I want to look at two different structured materials. I want to design them to the 5% LEL and compare them to, and because now I'm doing a design equivalent. Well, that's true when you're looking at materials that have the same or similar coefficients of variation, but it's not when you're looking at steel and wood, and we'll see on this particular slide. So in the bulletin, they took a class 4 pole. The yellow is representing alternate materials such as steel with 5% COV. The solid blue is wood with the expected COV of 20%. So So if you want to look at those two different materials and, to the same design using that 5% lower exclusion limit strength value, that design equivalency is where it meets here at that first dotted line. And visually, you can see that steel structures are less likely to fail at or below the design load. But again, what are we concerned about when we're talking about resiliency, hardening your system? You're talking about widespread failure, the big storms, the big issues. And so what they did is they performed statistical calculations based on 25% above what that design load was. How are these structures going to perform? And 99.8% of the steel structures are going to fail over less than 21% of the wood structures because of that COV. Now, I say that because...
Don't break theory.
What's that?
Bend but don't break theory.
Yes, well, I mean, the thing with that is I think from an engineering perspective, you have your known, right? You know that it's going to go, you have a small window where you have very high confidence level. The problem is how high are you going to design that and what level of storm are you going to design it to? And at what point does it become cost effective, right? And so, yes, you have, a narrow design for that 5% coefficient variation, which typically is looked at as a positive. What we're looking at here, we actually think the 20% COV is the positive for what we're facing today. It's storms. It's just a different way of looking at it, but it's real. So in our opinion, if utilities want to harden their system, the use of wood poles designed to higher loads rather than alternate materials is going to result in a more reliable system due to that greater inherent overload capacity of wood poles. Some utilities are used to and require an engineered manufactured product. That's great. We can do that in wood too. Laminated wood utility structures should be considered all the way up to 345 kV. It's an engineered product, 60 plus years service life, can be climbed with the standard hooks and drilled with regular equipment that they're using now. You can do multi-piece poles for storage, transportation, and installation purposes, just like the other industries like steel and composite. Manufactured to handle virtually any load and any length. Lead time is consistent because of the availability of the raw materials. You get the easily modified in the field, just like regular wood poles are. It's manufactured from renewable and sustainable wood resource, climate positive, carbon negative. Bottom line is laminated wood structures will compete with any other manufactured and engineered product out there, both on price and life expectancy. So, all right, Chad, are we going to have wood poles? Are they going to be available? Yes, they're available from the start of the utility industry. They're here today, and they're going to be into the future. And the reason why is the following. Growth exceeds harvest by 49% on our commercial timberlands. Every tree harvested is replaced. 1.7 million trees are planted every day. And that forest land base is stable. There's as much land in forest production as was back in 1900s. It's an extremely well-managed industry. We have, 14, 15 different foresters on our team. Part of their job is when we go in and we bid on these projects is to make sure that they're planting the proper species to make utility poles. Everybody's replanting, but it's a matter of educating and making sure that, that's renewable. And we have a dedicated team to do that. So lastly, we're going to talk about cost. Equivalent loading cost savings. And these are just two minor examples here, but customer had a 69 kV transmission line with 34 structures on it. You're looking at, when I say equivalent loading, so the line was designed with wood, like a class 1 65-foot structure, okay? The light duty steel was wood pole equivalent. In that particular case, when you compete against wood pole equivalent steel, 48% savings. Now, a utility could have used that savings to improve their right-of-way clearances and thereby reducing that likelihood of secondary damage like fallen trees and wind-blown debris to make that line more resilient, hardening the system. Another way of looking at it is actually increasing that reliability through value engineering. And so what we're looking at there is taking a class 1, right? They're both the same, class 1 load-bearing capability, but harden the system by increasing it not only one class, but 2 classes, and still be at a lower cost than steel. So you're increasing that lateral load at the tip by 36 to 42% at a lower cost than steel, making those lines safer with wood. Lastly, this slide here is talking about, the availability and the, being able to use certain materials at different voltages. I think one thing that is often missed, the further south you get, and southeast, is that they're more used to the southern yellow pine species. Southern yellow pine, you're not gonna get huge poles. Like you're gonna get 70-foot, 80-foot, maybe class ones, not in huge quantities, but in coastal Douglas fir, you can and you will. We can treat up to 130-foot pole in one section, up to a class H6. Those poles are available. And they can be utilized. So knowing that, in this particular ebook that I'm referencing, really looked at material comparisons and their compatibility, right? Obviously, on here, they're going all the way for wood, all the way up to 345 kV. Now, engineering and line design and the criteria is going to play a major factor. How long are the spans? Are we looking at monopoles? Are we looking at H-frame poles? All those things are going to factor in. But the fact of the matter is the balanced approach. You're going to need to use steel at certain points in the infrastructure. But when you can utilize wood, with all the benefits that come with wood, why not? So in summary, life expectancy, wood and steel have similar life expectancies and both need to be properly maintained out in the field. Trends are showing the intensity of weather events across the country growing, and we can increase that ladder load at the tip by 36 to 42% at a lower cost than steel. The materials you use impact the environment, and utilities with those carbon reduction initiatives should record the material carbon footprint. The availability, this is a renewable resource. It is available. And our challenges to utilities is, let's pick a project and work together. We talk about, changing buyers' behaviors, right? Fluorescent, whatever it be, LED lighting or whatnot. The challenge I have to the utility industry is, if we're serious about affecting climate change by reducing our overall emissions, changing our engineering behaviors to design lines using wood to make a positive impact on the environment. And with that, does anybody have any questions?
Chad, I know that our company is not planning on not using wood. The only thing that we're looking into now is we transitioned from creosote to CCA. CCA gave us a set of problems that, not from the usage standpoint, but from a disposal standpoint.
Yeah.
Interestingly enough, the EPA has exempted CCA poles when they're used as poles as hazardous waste. However, at the useful end of their life, if you decide to chop that pole up or burn it or whatever, it's hazardous waste.
Yeah.
So you only get the exemption when it's in its pole form. Bottom line, so that changed things up for us a little bit.
Okay.
From a disposal standpoint. So right now we're still recycling as many of our poles as we possibly can, our used poles.
Yep.
And CCA is good for that because obviously in that pole form, and it's still used in the pole form, it enjoys that exemption. However, what we have been incurring with us is CCA poles are very, what I would call conductive. There's so much chrome and copper in them that we're experiencing a lot of fires.
Okay.
And not only the fires kind of like spread all over the pole, especially when the conductors hit or whatever. When we first started using them, I think we had bad technique. The conductors were hitting too much, and we were experiencing a lot of fires. But now we know that they catch on fire easily, so we're taking precautions for that.
Okay.
But now we're thinking about transitioning again to the phenolic compounds and the less environmentally problematic formulations, I should say.
Copper naphthenate or DCOI probably?
Yeah, and so, but we're definitely planning on using poles well into the future. It just makes sense.
Yeah, I think the challenge that we run into is, with all the storms and the publicity of, hardening your systems and stuff, a lot of reaction to that was, well, we're moving to steel. And if a utility chose to use, to move to steel, it's very hard to get them to relook and reconsider. Again, it's not that you're not gonna utilize steel in infrastructure, it's a matter of when you can use wood, why not?
Yeah, and that's our philosophy, I
Yeah.
mean, you know, first of all, sometimes it just doesn't make sense, especially in residential areas, things like that. You know, there's obviously hurricane proofing and things like that, you'll see a lot, like I know, I have a house in Florida, they use concrete quite a bit in
Yep.
Florida.
Mhm.
You know, for the hardened infrastructure, that type of thing. But Texas is just too big, so we're gonna use wood.
Yeah, yeah. Cool.
I also want to say that it's a great point, just that, like, I've never thought of it in this way, the CO2 or carbon sequestration in trees, because typically whenever you hear carbon sequestration, you think geostorage.
Mhm.
So I thought that was interesting and a really good point too.
Yeah, I think, being in the wood industry, I'm out of my realm talking about environmental things. It's not something I don't normally do. But one thing that this slide that we created in a very short period of time that doesn't get into is the whole benefits of managing forests. So, the whole idea of, when you start talking affecting climate, if we're not managing our forests, at one point in time, the forests are going to start dwindling, not growing. And keeping that stable is really important for the environment. So, but I appreciate that. Yeah, I think it's just a reaction from the industry of promoting itself, and with those technical bulletins, I've developed more information just to educate the consumer. So,
Well, we certainly plan on leveraging our transition to a less environmentally toxic material. So we're planning on making sure that people know that that's what we're gonna be doing.
yeah, you gotta let them know,
We're gonna let them know. So, because, obviously the industry standard availability, one of the reasons we switched from creosote was not because it was an inferior pole, it's just that people weren't making them anymore. I mean, Texas was one of the last bastions of creosote poles, and that supply dried up, so we were kind of forced into doing, something different. And so CCA was the answer for now, but now, some of our engineers are using their environmental, thinking caps and looking a little bit past these things. And we're very pleased with that, because we are the environmental group at Encore. And so we do push these thoughts to our engineers, and sometimes it falls on deaf ears, but sometimes it actually hits home, and some of our younger engineers are really coming across with those.
Oh, that's great. Yeah, that's super.
We're excited about that.
Cool. All right, well, thank you.
Thank you, Chad. Thank you.
Thank you. Can I get you?
Yeah, I wanna just, well, I'll catch up with him.
Oh,
But
go
yeah.
ahead, go ahead. No,
No,
you're good.
that's okay, because he's already on, but yeah, and we're doing, I work with, I work in the environment.